All right, here we go, part 2. Kate, you missed out on the code red. Okay, but I know you're worried, but we're all okay. Thanks for not watching. Thanks for the concern. All right. So we go now and we look at the power surge. I think turned my camera off. I probably needed to do that. I probably need to turn that off. It's probably code red. Okay, so when I'm looking here, based on the data table above, which of the following liquid has the weakest intermolecular force? Weakest intermolecular force is going to be the highest vapor pressure. Okay, which is going to be C. Why are we saying A?
I don't know. That's wrong.
What's the biggest number?
92.
92. Okay? There is a chart. Now look, let's pay attention to something on this. Look. Okay, refocus now. We got 15 minutes. If I'm going to look at this, if I did not have this chart, I'm going to look at this and I'm going to say, ooh, these have hydrogen bonds. They're going to have the strongest attractive forces. They're going to have the lowest vapor pressure, okay? Not the highest, but CH3OH has the highest. Why do you think that can be compared to a C6H6 and a C2H6O, okay? I mean, how can those not be, how can this be the highest vapor pressure? Which means the weakest attractive force when it's got hydrogen bonds. Finally got quiet here.
Attention, since this time the drill has ended, we can resume normal activities. Thank you for your participation.
CH3OH is very small. Okay, just let it be. Let it be.
Yes, I
Okay.
can.
Okay, look, CH3OH is very small. So as these bigger molecules, they have stronger London forces. So we always have to, data dominates over what the theory says we want to look at, because there's conflicting things. As the molecules get bigger, your LDFs get larger. Yes, hydrogen bonds are the strongest of the three, but as this small molecule versus the large, we would say then that the LDFs of C6H6 are stronger than the combined LDFs dipole-dipole and hydrogen bonds of CH3OH, as evidenced by the difference in the vapor pressures. The relationship that I just gave you is always true. That always dominates. The highest vapor pressure is the weakest attractive force. Okay? That's huge. So we can't just always go by, oh, it's got hydrogen bonds, therefore it's got the strongest attractive force. We have to look at the data. Okay, that's going to be a problem. Okay? So now, let's look at number 9. No, we got to go back to number 7. Number 7. We never did this one.
You did
I think we did, sir. We did 8.
We ate
I know. Then we skipped. We skipped.
You said it was 8.
So what's the answer to 7? Why?
Because he said it was going to take you a long time to do it.
I know, because I haven't done it.
No, we didn't. We done it.
Oh. Okay, so hey. Okay, stop.
Oh my God.
Okay, stop. Somebody tell me the reason, the rationale. What's the main concept then behind number 7?
Coulombic contraction.
Coulombic attraction. Okay? Anytime there's a positive to negative, there's Coulombic attractions. So we do look at number 9. Okay? Now, which of the following best helps to explain why the value of delta H for the dissolving? Now, this is where I need you to get your notes out, where we look at factors that affect the maximum solubility. Okay? Factors that affect the maximum solubility. And the first one is temperature. When we look at our delta H of solution, it's going to equal delta H1 plus delta H2 plus delta H3. Now, we talked about these delta H1, 2, and 3. This is the steps of the solution process. This is our solute to solute. Okay? And in an ionic compound, what energy, what force do we have to overcome? The lattice energy. And we use Coulomb's law for this one. And then for covalent compounds, what do we have to overcome? IMFs. Okay? What's the sign of, yes sir?
Is delta H just the energy it takes?
The energy it takes, that's what H stands for, heat or the energy.
The energy to break it
To
apart.
break the ions apart from one another. That's the lattice energy that you got to put in. Is that going to be positive or negative? Breaking up is always hard to do, always requires energy. Anytime you break a bond of any kind, no matter whether it's a ionic, covalent, you know, the attraction between water molecules and the ions that we talked about in the previous one, anytime you break a bond, it requires energy. Anytime a bond is formed, it releases energy. Okay, let's focus. None of this is on there. Okay? So, this is always going to be, and I'm just going to put it up here, it's a positive delta H. It's always going to be positive. Now, delta H2 is going to be which one? Again, but what's the step? It's the solvent. Now, this one is the energy needed to move the molecules apart, the solvent molecules apart. This one's going to be pretty minimal. So we're really not going to worry too much about this one, but would it be positive or negative? It too is going to be positive. Okay? Now what's step 3 then, delta H3? Solute, solvent. This is where we talked about all the different types of attractive forces between the solute and the solvent. I gave you a little handout. Okay? What's the sign going to be? Negative. And we're always going to refer to this as the energy of hydration. The energy of hydration. So what's going to determine the overall sign of delta H?
Whether 1 or 3 is greater.
Whether 1 or 3. We're going to keep this minimal, so we're going to compare 1 and 3. Okay? Now, if delta H is positive, which one obviously is bigger?
1.
Delta H1. Okay? Delta H1. When I'm reading this right here, it says, first off, the dissolving of calcium fluoride in water. So what does that mean about calcium fluoride? Is it soluble in water?
Yes.
Yeah. Okay, the prompt itself tells you that it's going to dissolve in water. A positive and negative heat of solution does not mean that it's not soluble. Matter of fact, most solids and liquids have a positive heat of solution when they dissolve in water. Most solids and liquids have a positive heat of solution. So that's not going to be the answer. Calcium fluoride dissolves as CaF2 particles. Do ionic compounds dissolve as molecules?
No.
No. How is calcium fluoride going to dissolve?
Ion.
What ions?
Ca.
I'm going to get Ca2 plus plus what? Is it gonna be F2? What am I gonna get? 2F minus. Because again, it's gonna be Ca2 plus, F minus, F minus. Okay, the F minuses are gonna surround the Ca. The F's aren't bonded. Are two negative things gonna be attracted to one another? No, like charges repel. So when it goes into water and it dissociates, these two things are not gonna bond together. So you're gonna end up getting a calcium Ca2 plus surrounded by water. And then you're gonna get two F minuses surrounded by water. F minus surrounded by water. And I'm out of space, but okay, so how many particles total am I gonna get? 3. One part, for every one you put in, you're gonna get 3 particles dissolved. Okay? So that's not gonna be true. Now, here's the debate. Calcium ions have a very strong ion to ion interaction with F minus ions in the crystal lattice structure. Which delta H are we talking about there? 1. We're talking about the energy in the crystal lattice structure that's holding it together. Versus here, calcium ions have very strong ion to dipole with water. What delta H is that talking about? 3. So which one's going to be stronger if it's a positive heat of solution? 1. If it was a negative heat of solution, what would the answer to this be? D.
So bonds store energy and breaking those bonds releases energy.
No.
How does that work?
When you break the bonds, you're putting energy into them because they now have the potential to come back. Okay? So energy goes in to break the bond. Now it's stored. If you melt an ionic compound, you have to put energy in. It now has stored energy. When that melted, recrystallized, it's going to release that same amount of energy back.
So the positive is the energy you're putting in.
Yes.
Then what's the negative?
The negative is the energy that comes out. Okay, when you burn a piece of paper, as the paper burns, who's got the magnets or whatever? It's doing all the clicking.
I'm trying to take a sticker off.
Okay, let's just not. Okay? So if paper burns, as the paper goes from paper to ash and gases, it's releasing energy. So the ashes have less potential energy than the paper did. Well, where did all that potential energy go? Well, it was the fire that went to the surroundings. So when something dissolves, like sulfuric acid, when you dissolve sulfuric acid into water, it's got an extremely high energy of hydration. The whole solution gets extremely hot. Well, the energy that when that water attaches to those H plus ions, that energy that's released goes to the water, goes to the beaker, goes to my hand when I'm holding it. It just goes to the surroundings. What makes this also confusing is you have two different things. You have the system and you have the surroundings. The law of conservation of energy says that as one goes up, the other's got to go down. As one goes down, the other has to go up. So we're always measuring the energy of the system. Delta H is always going to be the energy of the system. But we're going to observe the energy of the surroundings. So if I say that something is absorbing energy, the system is going up. Well, where did that energy come from? The surroundings. So the energy of the surroundings went down, the surroundings got cold. For instance, you have a disposable ice pack in a first aid kit. Have any of y'all ever seen those? They got two different liquid in a pouch, and you break them and let the liquids come together. Well, it gets real cold. That means it has a positive heat of solution. So as they mix them together, it takes energy for those two things to mix together. So the lattice energy, or there's probably it's ammonium nitrate, so it's the lattice energy is real great. And so as a result, the surroundings though is the rest of the water, your ankle, the ice pack, and so The surroundings are putting the energy into the system, so the surroundings get cold. That's what makes it, we can't really see the system, we just know the surroundings.